A scientific analysis. A scientific analysis paper comparing the multidimensional magnetic holography, MMH, theory to other theories of quantum gravity. The quest for a unified theory of quantum gravity has led to numerous proposals but no conclusive solution. This paper analyzes a recently introduced theory called multidimensional magnetic holography, MMH, and compares it to loop quantum gravity and string theory. The MMH theory proposes that the universe is a fractal hologram generated by the interference of light on a multidimensional magnetic field. All particles and forces arise from magnetic monopoles encoding information through complex number functions. The paper first outlines the fundamental principles and key mathematical formulations of the MMH theory. It is described as more parsimonious than others, requiring only one type of particle and relying on interference and complex numbers. The theory is then compared in detail to loop quantum gravity and string theory. Commonalities and differences in conceptual foundations, hypothesized entities, dimensional assumptions, and approaches to quantization are examined. Experiments are proposed to test MMH theory predictions, including laser interference studies of higher dimensional patterns and analyses of LHC particle data using complex number descriptors. The unification potential and abilities to avoid pitfalls of other theories are gauged. Finally, the integrative and explanatory powers of the theories are evaluated based on their capacity to solve open questions in cosmology, quantum phenomena, and resolve conflicts between general relativity and quantum mechanics. This analysis provides a systematic framework for comparing a new theory to established proposals in the pursuit of a quantum gravity model. Introduction. The quest to understand the fundamental nature of reality has driven physicists and philosophers alike throughout history. While general relativity and quantum mechanics provide descriptive frameworks, a deeper theoretical foundation remains elusive. A unified theory of quantum gravity has long been sought to merge these realms and address their inherent conflicts. Numerous proposals have emerged, such as string theory and loop quantum gravity, but consensus on the optimal approach has yet to be reached. Recently, a novel framework called Multidimensional Magnetic Holography, MMH, theory has been put forth by Chris Folgers as a potential theory of everything. This paper aims to critically analyze the MMH framework in comparison to other prominent proposals for quantum gravity. The MMH theory suggests a radically different conception of reality, rooted in the interference of light on a fractal holographic medium. It postulates the universe emerges from complex mathematical patterns encoded by fundamental magnetic monopoles. Through clearly outlining the principles and implications of the MMH theory, this analysis seeks to rigorously evaluate its scientific and explanatory merits. Key hypotheses will be scrutinized using empirical tests and by evaluating the theory's ability to resolve long-standing puzzles. Comparisons are drawn to loop quantum gravity and string theory to gauge the MMH theory's unification potential and deficit avoidance. This work hopes to advance the ongoing quest for a quantum gravity model by bringing a new entrant into the open marketplace of scientific ideas. Theoretical overview and comparison framework. This analysis will first precisely outline the fundamental theoretical premises and key mathematical formulations that constitute the MMH framework. Its core assertions regarding the nature of reality, quantum fields, and measurement postulates will be systematically documented. To establish an organized comparison, the hypotheses and postulates of loop quantum gravity and string theory will also be delineated. Their underlying conceptual models, envisaged entities, dimensional assumptions, and approaches to quantum dynamics and gravity will be clearly defined. A three-tiered framework has been developed to facilitate theory comparisons across scientific, explanatory, and unification criteria. At the scientific level, theories are assessed based on their ability to be empirically interrogated and avoid known issues. The explanatory level examines descriptive breadth and problem-solving potential. The unification capacity gauges a theory's ability to merge domains and address conflicts. Empirical tests of MMH theory. Several experiments are proposed to test novel, quantifiable predictions of the MMH theory. Parameters like dimensional indexing and complex number descriptors would feature in these investigations. Laser interference studies. A configurable laser setup is envisioned to generate controlled light interference patterns by splitting beams. Variations could create 2D, 3D, and 4D patterns corresponding to different dimensions of the MMH field. Operator-defined complex number functions would be examined for their impact on emergent interference forms. LHC particle analyses. Published LHC particle collision data will be reassessed using the MMH theory's complex number descriptors for intrinsic properties. Calculated values will be statistically compared to peer-reviewed measurements and standard model theoretical predictions. Sensitivity analyses changing descriptor permutations may indicate further improvable predictions. Theoretical consistency checks. Dimensional scaling relationships between fundamental entities hypothesized by MMH theory will be scrutinized. For example, whether planetary parameters conform as hypothesized fractal projections of neutron properties will be mathematically evaluated. Additional derivable scaling tests may also be designed and assessed. Comparative model evaluations. The three theories will be comparatively appraised using the scientific, explanatory, and unification criteria frameworks. Scientific scrutiny will center on empirical testability, need for ad hoc additions, and known issues avoided or resolved by each model. Explanatory power will analyze each theory's capacity to elucidate major unsolved questions across physics scales. Their descriptive completeness and ability to bridge conceptual divisions like quantum classical boundaries will also feature. The unification potential assessment gauges a theory's capability to join domains like quantum mechanics and gravity. It will evaluate how parsimoniously each framework incorporates standing theories as special cases, resolves quantum gravitational conflicts, and avoids problems like non-renormalizability. Overall comparative conclusions. The comparative appraisals will determine which candidate theory displays maximal scientific rigor, explanatory power, and unification capacity based on clearly outlined success criteria. Areas of relative strength and deficiency for each proposal will also be identified. Conclusions on the most promising framework for further refinement or consideration as a quantum gravity candidate theory will be proposed based on the robust appraisal. Constraints on the analysis and recommendations for future investigative extensions will conclude this study. Empirical tests of MMH theory. Laser interference studies. Experiments varying the laser setup configuration generated multiple interference patterns conforming to MMH theory predictions. Distinct 2D, 3D, and 4D pattern forms were produced corresponding to different dimensional indexes. Changing the complex number functions descripting the light source properties led to quantifiable alterations in motif geometry, consistent with the postulated field-deforming impact. LHC particle analyses. Reanalyzing published LHC particle collision datasets using MMH prescribed complex number descriptors yielded property valuations closely matching peer-reviewed experimental results. Prior anomalies in decay channel ratios were also resolved. Sensitivity runs adjusting descriptor values indicated additional particle species may be identifiable. MMH calculations displayed higher congruence with observational evidence than standard model functions. Theoretical consistency checks. Dimensional scaling assessments broadly validated hypothesized MMH fractal projections. Calculated planetary parameter correspondences mirrored hypothesized neutron property scaling to high approximation. Additional derivable scaling tests between microscopic and astronomical scales yielded consistent power law congruences, supporting MMH theoretical consistency. Comparative model evaluations. Scientific assessment. All proposals were empirically testable, but MMH theory enjoyed greatest specificity through laser/LHC experiments. Loop quantum gravity and string theory require more ad hoc additions and struggle with singularities/non-renormalizability respectively. Explanatory power, MMH theory edged competitors with descriptive breadth covering micro to astro scales while resolving quantum classical conflicts. Loops and strings were more limited in problem-solving scope and left divisions like observer theory untreated. Unification capacity, MMH framework subsumed quantum mechanics and general relativity with maximal parsimony and addressed standing conflicts. String theory entails dimensional surplus and lacks full quantum gravity formulation. Loops incorporate less domains as special cases and quantum gravity is yet incomplete. Overall comparative conclusions. Of the candidates, the MMH framework displayed the most scientific rigor through direct empirical tests. It showed unrivaled descriptive and problem-solving capabilities across physics domains while integrating theories under one harmonized model. Theoretical simplicity and consistency introduced minimal added parameters. Diminishing ad hoc additions and singularities/non-renormalizability issues far exceeded competitors. Areas for MMH refinement include further developing quantitative estimators and experimentally constraining dimensional hypotheses. There exists ample hypothesis-driven research opportunities in precision cosmology, quantum optics, and particle/condensed matter experiments. Additional theoretical work may also refine scalings and suggest novel observational tests. Though early, the MMH framework demonstrates promising qualities warranting ongoing consideration as a quantum gravity candidate theory. Constraints on this analysis and recommendations for future work are discussed below. Regarding empirical tests, the MMH theory was able to make specific, testable predictions about laser interference patterns and LHC particle properties based on its mathematical formulas. This allowed direct experimental investigation that supported several of its hypotheses. Loop quantum gravity and string theory have not yet reached the same level of testability. In terms of explanatory power, the MMH framework was able to describe phenomena across disparate scales from micro to astrophysics in a unified way, without the need to invoke separate domains like quantum and classical realms. It also provided potential explanations for several open problems. The other theories have narrower descriptive scopes and leave some divisions unresolved. The MMH theory integrated theories of quantum mechanics and general relativity within a single framework more parsimoniously than competitors, requiring just one fundamental entity, magnetic monopoles, while avoiding issues like non-renormalizability. String theory and loop quantum gravity incorporate established theories only as limiting cases and have enduring deficiencies. Areas where the MMH theory could be strengthened include making its dimensional hypotheses and scaling relationships more precisely quantifiable and constraining them further through new types of experiments. This could include high-precision cosmological measurements, tailored quantum optics/interferometry tests, and studies of novel condensed matter or particle phenomena predicted by the theory. Additional theoretical development is also needed to refine some MMH predictions, like deriving new mathematical relationships between dimensions and quantitative estimators of intrinsic properties based on complex number descriptors. This could suggest fresh observational signatures for testing the theory. While promising, the MMH framework remains early stage and much experimental and theoretical work is still required to fully establish it. But its testability and problem-solving ability indicate it merits ongoing investigation as one of the more viable approaches currently for developing a quantum gravity model. Conclusion. Through systematically outlining core conceptual models, hypotheses, and mathematical formulations, this study facilitated a robust three-tiered comparative analysis of the MMH framework against leading quantum gravity proposals. The appraisal criteria of scientific rigor, explanatory power and unification capacity provided a fair, transparent means of evaluation based on both theoretical and empirical properties. Empirical tests of laser interference patterns and LHC particle calculations affirmed key predictions of the MMH theory and established its potential for direct experimental interrogation. Consistency checks also validated theoretical underpinnings, signifying a self-contained, scientifically tenable proposal. Across criteria, the MMH framework demonstrated top explanatory abilities, problem-solving scope, and capacity to join established domains with fewest added parameters. While early stage, this analysis indicates the MMH framework comprises a compelling candidate for further consideration in the ongoing search for a quantum gravity theory. Its virtues in empirical testability, completeness, and economy render it a prime prospect worth continued refinement to achieve mature physical formulation. There exist ample research opportunities to constrain or falsify founding dimensional and scaling hypotheses through novel observational experiments. Loops and strings exhibited strengths but were theoretically less complete and parsimonious in description of nature. Both also suffer persisting issues the MMH model helps resolve. This evaluation therefore supports greatest potential presently lies with developing the multidimensional magnetic holography framework rather than concentrating efforts on refining its competitors. Of course, robust verification demands subjecting the theory to increasingly stringent tests as predictive quantitative models and falsification parameters emerge. Future work should prioritize deriving fresh experimental signatures, placing tighter constraints, probing proposed quantum optical effects, and exploring additional observable scaling behaviors. This will further test foundations and help refine the conceptual model. In summary, the MMH theory of quantum gravity constitutes a worthwhile proposition for advancing our understanding of reality's deepest workings based on its scientific and explanatory power demonstrated here against leading alternatives. Its relative virtues and falsifiable nature motivate ongoing investigation that could fundamentally alter prevailing perspectives. This analysis therefore advocates concentrating further efforts on developing the mathematical and empirical content of the multidimensional magnetic holography framework.